Hi everyone. We're going to be finding the volume of high-dimensional balls using only low-dimensional calculus. Equation 1 is the formula we're looking for. It gives the volume V sub n of r of an n-dimensional ball of radius r. You'll notice that this formula is piecewise and gives two different expressions depending on whether the dimension of the ball is even or odd. Here are the formulas for the first 6 dimensions. You have ordinary length, area, and volume in the first row. In a bit, we'll talk about how we can interpret all these quantities as volumes in their own right. At an intermediate point in proving equation 1, we're going to show that the limit as n goes to infinity of the volumes of balls of radius 1 is actually 0. That's pretty clear from equation 1 because factorials outrun exponentials, but it's neat that we can show this well before we've actually verified the main result. This talk is intended for those who've had standard multivariate calculus and are familiar with proof by induction. What we're going to do is extend the univariate disk method for 3D volumes of revolution to arbitrarily high dimensional volumes. The approach is essentially inductive, which means we get lower dimensional information and produce higher dimensional information jump-started by initial dimensions 1 and 2. So we're motivated by single variable material, and our work will build on itself very naturally. There are not going to be any left field or unexpected ingredients appearing, such as the Gaussian curve or the gamma function. More advanced proofs are very cool and have a lot of stuff going for them, but they're not really what we're shooting for in this video. What we're going to do will be very minimal as far as the algebra and calculus are concerned. For instance, no high-dimensional spherical coordinates or anything that's going to be really computational is going to show up. What do we mean by n-dimensional space and balls? We're not talking about anything in physical reality. One-dimensional space for us is simply the set of all real numbers, the number line. The plane, or two-dimensional space, is the set of all pairs of real numbers. Three-dimensional space is the set of triples of real numbers. Four-dimensional space is the set of all quadruples of numbers, and so on. The distance from 2 points x and y in n-dimensional space is still given by a version of the distance formula, which is the Pythagorean theorem in disguise. So it behaves in many ways just like the distance formula you've seen in your classes up until now. An n-dimensional ball of radius r centered at 0 is the set of all points whose distance from 0 is no more than r. So the same geometric idea that you use to define a circle or a sphere continues into higher dimensions. Therefore, a one-dimensional ball is a line segment, a two-dimensional ball is a filled-in circle, a three-dimensional ball is a solid sphere, and so on. Also, when we refer to a unit ball, all we mean is a ball of radius 1. So what do we mean by n-dimensional volume? Going with what we already know, one-dimensional volume is length. That's straightforward. Two-dimensional volume is area, as you've seen in Cal 2. You can break shapes into tiny squares and rectangles and take limits. Three-dimensional volume you've seen in Cal 2 and also Cal 3. You break shapes into tiny boxes, shells, disks, whatever the case may be, and you take limits. Moving to higher dimensions, the volume of an n-dimensional box with side lengths L1 through L sub n is simply the product of all of the lengths, and these are your basic units in n-dimensional space. For higher dimensional volume, you just break your shape into small n-dimensional boxes and take limits, so it all works out the same way. Conceptually now, length is 1D volume, area is 2D volume, and what you typically think of as volume, we call that 3D volume. We're going to quickly review the slice method for 2D volume, which is area, and 3D volume. The area of a region in the plane with height h of x, as x varies from a to b, is just the integral of h of x from a to b. That is, we can say a one-dimensional height sweeps out a two-dimensional area. Similarly, the volume of a region in space with a cross-sectional area a of x, as x varies from a to b, is given by the integral from a to b of a of x dx, and a two-dimensional area sweeps out a three-dimensional region. This is illustrated in the following figure. Keep in mind that we are still using a univariate calculus approach to finding volume. We're set to generalize the slice method to higher dimensions. An n-dimensional figure, which is just a subset of Rn, has n-1 dimensional cross-sections, just like a three-dimensional figure has two-dimensional cross-sections. These n-1 dimensional cross-sections sweep out the n-dimensional figure. Proceeding by analogy, if the cross-section has n-1 dimensional volume depending on x, which we write as vol sub n-1 of x, then the n-dimensional volume of the figure is simply the integral of this n-1 dimensional volume. I'm being a bit fuzzy on the nitty-gritty details, but all of this can be made completely precise with measure theory. Now let v sub n of r be the n-dimensional volume of an n-dimensional ball of radius r. A point inside an n-dimensional ball of radius r with coordinates x sub 1 through x sub n-1, where the nth coordinate is x, satisfies this equation here. This is just the equation of an n-ball where we subtracted the last coordinate squared from both sides. Now for a given radius between -r and r, the cross-sections of the n-dimensional ball are exactly the n-1 dimensional balls of radius root r squared minus x squared. By equation 2, we can integrate these cross-sectional volumes to get the entire volume. Note that we need to use this when n is greater than or equal to 2 because we're starting off with information about v sub 1, and that's what happens here when n is equal to 2. Since v sub 1 is 2r, this equation lets us find v sub 2, then v sub 3, then v sub 4, and so on. An important point is that all reasoning will be based on equation 3 from here onward to make everything rigorous and airtight. The volume of an n-dimensional ball scales with r to the nth power, and we can write the volume of an n-dimensional ball of radius r as the volume of a unit ball times r to the n. As it happens, equation 4 is the key that unlocks all the upcoming calculations and keeps the algebra manageable. Equation 4 is evident in dimensions 1, 2, and 3, and it's certainly plausible in general to gain a power of r with each dimension that you add to your ball, but we still need proof. Induction is definitely the way to go, and it's a nice proof and good to see. Proceeding by induction, the base case is clear. Now for the inductive step. We just need to show that if the formula holds for all n-dimensional balls, then it holds for all n+1 dimensional balls. Assuming the inductive hypothesis, by equation 3 that we're basing all of our proofs on, it's enough to show the equality below holds because this is just the formula for volume of the n+1 dimensional ball of radius r. Starting with equation 3 into u substitution, we get the following expression for v sub n+1 of r. Here, using equation 3, apply the u substitution and pull r out of the square root. We can apply the inductive hypothesis and then use the rules of exponents and the inductive hypothesis again to completely remove r from the inside of v sub n. When we plug this into equation 5 from the previous slide, we get exactly what it is we're looking for and complete the inductive step. By the principle of mathematical induction, we know that the scaling equation holds for all values of r and all integers n greater than or equal to 1. At this point, we already have enough to examine the limiting behavior of v sub n of 1. The scaling equation 4 shows the following relationship, where we're also using an exponent rule on the right-hand side. Combining with equation 3, we can replace the integrand with the right-hand side of the above quantity, which is very cool. Therefore, the volume of the nth unit ball is the volume of the n-1st unit ball times some integral quantity. Now, when n is greater than or equal to 7, we have v sub n is less than or equal to v sub n-1 times this integral. Why? Because if n is made smaller, we're actually making the integrand bigger, so we can replace this equality here with an inequality in this direction. When the integral is evaluated, which is easy to do since it's a polynomial, we get v sub n is less than or equal to v sub n minus 1 of 1 times 32 over 35. Iterating this down n minus 7 times, we see that v sub n of 1 is bounded by a geometric sequence that decays to 0 in the variable n. So by the squeeze theorem, the limit is 0. This is very neat because we haven't really used any heavy machinery to get to this point. It's worth noting that the convergence here is actually faster than geometric, but it's still cool that we're able to get convergence to 0 in the first place. Moving on to our main goal, we need to choose a good inductive approach to get the final formulas. Recall equation 6 from the previous slide. This gives the volume of the nth unit ball in terms of the n minus first unit ball while multiplying it by this integral. What we won't do is compute this integral and iterate to get the final formula. Why is that? This integral winds up involving quite a bit of algebra, because when n is even, then the exponent in the integral is not an integer, as opposed to the case when n is odd. Therefore, we'd have to deal with two cases, integral reduction formulas, and a symbolic mess. This approach works, but it's not pretty. Alternatively, what we will do is develop and use a result similar to equation 6 with an easier integral that gets the volume of the n-dimensional unit ball from the volume of the n minus 2-dimensional unit ball. We'll have to go a bit beyond univariate techniques, but we won't have much algebraic clutter. In particular, this method lets us uncouple the odd and even cases, and the single variable integral that we eventually get is easy to compute. Let's implement this idea. Let n be greater than or equal to 3. By equation 3, which is the foundation we're building on, we have equations 7 and 8. Equation 7 is what happens when r equals 1 in equation 3, and equation 8 is what we get when we sub r equals the square root of 1 minus x squared into equation 3. When we plug the right-hand side of equation 8 into the left-hand side of equation 7, we get the nice double integral in equation 9. Why is it nice? Because equation 9 is perfectly suited for integration by polar coordinates, since the region in the xy plane is a disk of radius 1. Converting equation 9 to polar coordinates means theta goes from 0 to 2 pi, r goes from 0 to 1, and dx dy equals r dr d theta. However, since there's no theta dependence in the integral, we get that the double integral is just 2 pi times a one-dimensional integral. As an aside, it's worth noting that when n is 3, equation 10 is exactly the shell method applied to finding the volume of a sphere of radius 1. Continuing onward, in order to use equation 10 for our purposes, we need to find a way to convert the integrand into a usable form. But this can easily be done with equation 4, the scaling relation for volume. By equation 4, we get equation 11. Subbing equation 11 into equation 10 gives us the nice equation 12. Let's sum up what we've done so far. The equation getting v sub n of 1 from v sub n minus 1 of 1 involves an integral that has a lot of moving parts if we tackle it directly, because the power of 1 minus x squared is not always a whole number. However, by introducing double integrals into polar coordinates, we get around this hurdle and obtain a recursion equation 12 for v sub n of 1 from v sub n minus 2 of 1, whose integral is easy to evaluate with the simple u substitution u equals 1 minus x squared. The presence of the x outside the parentheses is what makes the whole thing go. We're ready to get the final formula for even dimensions. If n is even and greater than or equal to 4, then we can set n equal to 2k where k is greater than or equal to 2. So by equation 13, we have equation 14. If we iterate equation 14 down to k equals 2, and use the fact that v sub 2 of 1 is the area of the unit circle, which is pi, we obtain equation 15. The full result when n is even and at least 4 follows from equation 15 if we throw the scaling equation 4 into the mix. The highlighted formula holds automatically when n equals 2, so we are done with the even case. The odd case is completely similar. If n is odd and greater than or equal to 3, then we can set n equal to 2k plus 1, where k is greater than or equal to 1. So by equation 13, we have equation 16. If equation 16 is iterated down to k equals 1, and we use the fact that v sub 1 of 1 is the length of the interval from minus 1 to 1, which is 2, we obtain equation 17. The full result when n is odd, and at least 3, follows from equation 17 when we use equation 4. This formula holds when n equals 1, since 1, k equals 0, and 2, the product in the denominator is empty and therefore 1 by definition. That does it for this video, but I plan on having more math content soon. Please let me know what you think in the comments and if there are other math topics you'd like me to talk about. If you liked this, please subscribe. Thanks for watching and have a great day.